Hello friends, welcome to today's lecture, the next lecture in the series Thermal History of the Universe. Daniel Bauman in his lecture notes says the transition from relativistic to non-relativistic behavior isn't instantaneous, and that makes sense. About 80% of the particle-antiparticle annihilations takes place in the interval when temperature falls from m to m over 6. And the same statement in a slightly different words appear in the notes from University of Helsinki. Particle antiparticle annihilation takes place mainly about 80% during the temperature interval m to m by 6. It is thus not an instantaneous event but takes several Hubble times. And I can show you the notes. This is from the University of Helsinki. So here is the statement. At lower temperature, the thermal energies are no more sufficient for pair production. Particle antiparticle annihilation takes place during the temperature interval when temperature falls from m to m by 6. And in the notes from Bauman, here is the statement. The transition from relativistic to non-relativistic behavior isn't instantaneous. 80% of the particle annihilation takes place in m to m by 6. Now let us prove this, let us verify this using Mathematica. So that 80% of the particles annihilate during the interval m to m by 6. So we would like to verify this using Mathematica. Number density is given by this expression, which we have seen before. And the chemical potential we can ignore in this calculation because chemical potential is mu over T term is negligible at all times for all particles during the history of the universe. So we can write approximate number density as this, where energy is equal to square root of p square plus m square. Now next, let q is equal to m over t. So we make this substitution in the integral, and once we substitute this in the integral, and then once we substitute this, what does this become? Let q is equal to, first thing is, I think we should do this substitution. X is equal to this. So then x is equal to square root of p square plus m square over t. Q is equal to m over t. And after some algebraic manipulations, we can write number density in this form. It's pretty straightforward. And integral goes from now q to infinity. Previously, it was p limits were 0 to infinity. So when p is 0, x is equal to q, and when p is infinity, x is infinity. So the integral goes from q to infinity, and number density comes like this. It's pretty straightforward. And I substitute q back m over t. So when I put m over t back in q, and becomes this, and number density is number of particles over volume. And so number of particles, volume is proportional to a cube. So we have some constant here times a cube, because volume is proportional to a cube, and g over 2 pi square can be absorbed in that constant. So we have a cube t cube, and then this, and at is roughly constant. More accurately, it is g star s a cube t cube constant. But for the present discussion, we can take at equal to constant, and then number of particles is given by some constant times this integral, and this is not x but constant times this integral, where I is integral, and integral is given by this. Now this integral, so number of particles is proportional to this integral, and let us solve this integral numerically. So I would write a function in Mathematica to solve this integral numerically, and q is which is m over t. Q is m over t, mass over temperature, that I pass as an argument to this function, and I can say that this is my function, some you can say number integral. So number integral, and I integrate numerically, and integrate means numerically integrate, and from q to infinity. This function gives me value of the number integral for different values of q, and I evaluate this at these temperatures. So first I take a very high temperature, 1000, when temperature is 1000 times mass, and then temperature is 500 times mass, 400 times mass, temperature drops, keeps dropping, and then temperature is 1 over 2 times mass, 1 over 3 times mass, 1 over 4 times mass, and all the way I take up to 1 over 8 times mass. So what I do is that I form a list of these values, which I can call list T over M. So this is my list T over M, and then so this is length of this list, and then this is number integral I evaluate at the first value, which is 1000, and that is the number relativistic number of particles when particle is relativistic. So this is the value which I am going to take for a relativistic scenario when temperature is 1000 times mass. So number relativistic, and I evaluate this. Let's start from here. Number integral, first of all, I okay, so this function is evaluated. Now I evaluate this block. Okay, so what does it say? Yeah, this variable has to be list T over M. Okay, let's reevaluate this. Now it is fine. So for I is equal to 1 to length plus 1 I plus plus, I'm going to evaluate this integral, which is basically number at given T over M. So I can say number integral and or you can give it some name like integral 1, and this number integral, or you can say number integral 1, which is number integral evaluated at this is for loop. I am iterating over this list, so number integral evaluated at the T over M value present in the list. And remember, Q is M over T. And this is T over M in the list. So this is number integral 1. So I'm going to now print the output. The integral value, the number integral value at T over M is equal to list T over M. So this is a value of T over M. And then whatever we get from this integral, we need to put this in the output. So it joins all these strings which I am passing to this function. This is if I don't call it like this, then Mathematica does not give proper string output. So I have to, in order to get proper string output, I need to call two string functions so that this numerical values get converted into proper string values. And then I concatenate, join all the strings. So toString converts numerical values into string values. And then I print. Let's see. There you go. So you see that at T over M, let me just you see that this font size is very small. So what you do is that you select this output block and then you say press Alt plus 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 until you get the desired font size. Now here you see when I start with 1000, I get 1.8, the value for that integral. And number density is proportional to this value. Number of particles is proportional to this. There is other factor also like A, T, and G over 2 pi whole cube, which is present as a constant before the integral. So this is the number integral value 1.803, 1.803. So you see that in the relativistic scenario, this integral value is almost constant. So 1.803 all the way up to 100 and up to 50, you see it is almost constant. At 50, it slightly drops to 1.8029. And at T over M equal to 5, there is again a slight drop from 1.8 to 1.78. Again, a slight drop from when temperature falls to 4M, 3M, 2M, and 1M. Now, to verify that statement, that 80% of a drop in particle number is between M when temperature falls from M to M by 6. So this is the scenario when temperature is equal to M. We see that number of particles is 1.515. And when it falls to M over 6, the number of particles is proportional to 0.06. So what is the percentage of this particle decrease in particle number? Let us evaluate that percentage decrease. And by the way, I changed the name of integral. Previously, I had written it, I had given it name A, but now I'm giving it more meaningful name, number integral. So number integral, this is when temperature is equal to M minus when temperature is equal to M over 6 and then divided by the relativistic number multiplied by 100. So decrease in number of particles from M to M by 6 is given by the numerator divided by total number which was present at the relativistic temperature multiplied by 100 will give me 80 point will give me the answer. And you see this is what I evaluated before this lecture, and I should get the same number. Let me remove this output so that you know that I'm not cheating. So I remove that output. Now I have clean slate. So I am going to evaluate this expression, and you see I get 80.6445. So 80% of drop in the particle number happens in this temperature interval when temperature goes from m to m over 6. 80% of decrease in particle number is in this range from m to m over 6. Okay, this was very interesting. Thank you very much. See you next time.